In this video, we're going to look at independent and mutually exclusive events. We're going to determine if two events are mutually exclusive. We're going to determine if two events are independent. And we're going to calculate conditional probability using the rules to calculate probabilities. So two events, these events A and B, however you want to label them, are considered independent when the occurrence or knowledge of one event does not impact the likelihood or the outcome of the other event happening. So as an example, if you're rolling a fair die twice, the outcome of rolling the first die does not influence the outcome of the second die. So to establish the independence of two events, all we have to do is demonstrate one of these three conditions. Either the probability of A given B is equal to the probability of A, or the probability of B given A is equal to the probability of B. Now notice that B, in this case, whatever is wrote second, has already happened, and you're just showing that the probability of A is the same as if probability of B never even happened. So when you see this notation, the thing that you see second with that after that straight line means that that event has already happened. So the probability of A, given that B has already happened, is equal to the probability of A as if B never happened. So either one of these, as long as either one of these is true, then we know they're independent. And then the third condition is the probability of both A and B happening is equal to the probability of A happening multiplied by the probability of B. And you only need to show one of those three things to show that they are independent. Now, if we can't show that or we're not sure, we assume to begin with that it is a dependent. And then also we're going to talk about with replacement and without replacement. So when we talk about with replacement, that after you pick something like you're doing a deck of cards, 52 cards, you pull a card out. With replacement means that you put that card back in. When sampling is done with replacements, the events are considered to be independent, meaning that the result of the first pick will not change the probabilities for the second pick. So without having to even prove any of this stuff, if we know it's with replacement, so we pull the card out, look at it, put it back, then it is going to be an independent. Without replacement, which means I look at the deck of cards, I pull a card, and I keep the card. That would be without replacement. These events are considered to be dependent or not independent. Okay, so Jose rolls a six-sided fair die. On his first roll, he gets a 3, and then he rolls again. What is the probability he will roll 3 on a second time? That is, what is the probability of he rolls a P after he's already rolled a P? So this is rolling a P given that he's already rolled a 3. What is the probability that he will roll a 6 a second time? That is, what's the probability of him rolling a 6 after he's already rolled a 3? Are these two rolls independent or dependent? Now, without doing any work, we know that rolling a die once and then re-rolling it again is not going to affect what the outcome is on the second roll. So without doing any work, we know that these are independent. So then what do we do to do the actual math part? Well, the probability of 6 given 3, I'll do that one first, is a probability of 6 and 3 divided by the probability of 3 already happening. And we know the probability of rolling a 6 and a 3 with two separate rolls is 1 in 6 for rolling a 6 and 1 in 6 for rolling a 3. And knowing that being able to roll a 3 is 1 in 6, so the answer is 1 in 6, which shows to us that this is also equal to the probability of 6 without even worrying about 3 ever happening. Same thing is going to be true if you do the probability of 3 given 3. So this is the probability of 3 and then a 3 on the second roll, and divided by the probability of 3 happening on the first roll. So it's 1 in 6 multiplied by 1 in 6 divided by 1 in 6, which we know is 1 in 6, which is the probability of rolling a 3 in the first place. On this example, we're asked to draw two cards from a standard 52 deck of cards with replacement. So without doing any work, we know that these are independent. Find the probability of getting at least one black card. Well, when I see the word at least, then that means I want no black cards. And the reason I want no black cards is because if I do 1 minus no black cards, I will get at least 1. So the probability of at least 1 black card is equal to 1 minus the probability of no black cards. Okay, so what's the probability on the first draw of no black cards? Well, the probability of no black cards is 26 out of 52 because there are 26 cards that are not black in the deck of 52. Now, we know that this is independent, right? Since this is independent, then the probability of no black cards on 2 draws, so the probability of no black cards on the second draw, no black cards, because this is independent, means that this is going to be the multiplication of no black cards twice. Should have just labeled this E. So in fact, that's what I'm going to do. I'm going to just make my life easy and say no black cards is E. So this is E. Probability of E, where E equals no black cards. Okay, because this thing is independent, then the probability of E happening, given that E has already happened, is going to be the probability of E happening multiplied by the probability of E happening, because they're independent, and that was from up above. And so this is just going to be 26 out of 52 multiplied by 26 out of 52. Now, that's not what I want. I want at least 1 black card. So this is what I want to do. I'm going to do 1 minus that 26 out of 52 multiplied by that 26 out of 52. And so the answer that I really want then is 1 minus 0.25, because 26 out of 52 is 0.5. So 0.5 twice is 0.25. And so we have a 75% chance, or the probability is 0.75. Now I just want to take a moment and say, when I see 75%, this is a chance of happening. Probability is a number between 0 and probability and 1. So when I talk about probability, the probability is 0.75. It's a decimal. The chance is 75% chance. So I just want to say I have a 75% chance of drawing at least 1 black card if I draw the cards twice. If I want to talk about chance, it's 75%. The probability is 0.75. Okay. So now, let's look at this example. Erase this. 48% of all Californians registered voters prefer life in prison without parole over the death penalty for a person convicted of first-degree murder. Among the Latino California registered voters, 55% prefer life in prison without parole over the death penalty for a person convicted of first-degree murder. 37.6% of all Californians are Latinos. In this problem, C is the Californians. Okay, so C, the probability of C is 0.48. It's 48%, but remember, probability is a decimal. And the probability of L, since L represents Latinos, California Latinos, is going to be 0.376. Okay, I'm just going to write that as L. Probability of L is 0.376. Now I'm just writing that because I don't want to lose what it is. Now, this is other information, and I don't have anything for that, right? I don't have anything, I don't have a C or an L. So in words, what is the probability of C and L? Well, the probability of C and L in words is a probability that I'm going to choose somebody that is a registered voter in California who prefers life in prison without parole, as well as the overlap of that person being a Latino. So in words, that's what that means, is that the probability of choosing a person in California that's a registered voter who prefers life in prison versus death penalty, and that person also happens to be a Latino that believes the same thing. Or just Latino, sorry, just a Latino. Okay, so now I want to find P and C. So P and C is the intersection of the Latino voters and the Latinos in California. So the probability of this overlap would be the fact that they are a Latino Californian, right? So we know a Latino Californian, so that's the probability of Latino Californian, which is 0.376. And now we're going to use this stuff, is the probability that they also believe. So not only are they going to be a Latino California, but they're also going to be a registered Latino California who prefers life in prison without parole versus the death penalty. So we didn't actually label that, so I'm just going to label this E. So E is going to be this. So even though I'm doing the probability of C and L, what I really want is the overlap, which is going to be the probability of Latino and they believe in life in prison. So 0.55. So this is actually going to be the probability of L multiplied by the probability of E, which is going to be 0.376 multiplied by 0.55, which is going to give me 0.2068. So in other words, I have 20.68% chance of getting a person that is both a California registered voter and is Latino and believes that there should be life in prison without parole over the death penalty. Okay, now, what is C or L? Well, C means that they're a registered voter preferring life in prison without parole over the death penalty, or they're a Latino. So the first thing I want to do is I need to find that intersection, right? So we know the P of C was the 0.55. The P of L was the 37.6 or 0.376. Now, the overlap we just had was this here. This was the overlap. So this is the overlap. So the probability, in this case, of P or C is the probability of the person being C, the probability of the person being Latino, and then minus that probability of C and L, which is the overlap. So in this case, it's going to be 0.55 plus 0.376 minus the 0.2068. And my final answer then is 0.64645, or I have a 64.645% chance of choosing somebody that is a California registered voter who believes in prison without parole over the death penalty, or is a Latino. Oh, that goes there. Now, in words, what does P choose, or P with this line, P of C, line, and L? So what this is the probability of the person being a California registered voter that believes in prison without parole over the death penalty, given that they are Latino. So that's what that means. So how do we do this? Well, we've already done most of the work, right? we know that this is going to be P of C and L divided by the probability of L. So P and C was that overlap, which was 0.2068. My L was, from before, was 0.376. And then this ends up being 0.55 or 55% chance. So that's that. Is this independent? No, this is not independent because P of C is equal to 0.48 or 48% chance. And for it to be independent, this P probability of C given L has to equal the probability of C, and this doesn't. So we know that this is not independent. Now let's talk about what it means to be mutually exclusive. Let me erase this. So independent and mutually exclusive are not necessarily the same thing. What mutually exclusive means is that the events cannot occur at the same time. That means that they don't share any outcomes. So the probability of A and B both happening is 0. They cannot happen at the same time. And we assume that they are not mutually exclusive unless I can show otherwise. So we make assumptions unless we can show otherwise. Now, if we go back to our previous example, 48% of all Californians registered. Is C and L mutually exclusive? And the answer is no. Now, even if I didn't know that, even if I couldn't reason through the fact that they're Californians and Latino Californians, the fact that they're both Californians means that they're not mutually exclusive. But I also know that P of C and L by up above was not equal to 0. So that proves that it is not mutually exclusive, even if I didn't reason through that. And that's it for this video.